Okay. So good evening everyone and welcome to the second live session for the course Measure and Integration. So just like in the last session, I'll first recap all the theories that you have learned in this week, and then I'll go for some problems related to those theory. Okay. Okay, so far what you have seen, so actually in the last tutorial or session I was just saying you that suppose you had this ring with measure mu, okay, that is the pre-measure. So while I was extending it, I was saying that it will extend to hr with the outer measure mu star, and then from there I'll do something to go, I'll define the set s bar, which is the set of mu star measurable sets, and then the measure mu bar will be just restriction of this mu star on that sigma algebra, that s bar, right? So this was the whole theory. So what I was doing earlier, that suppose we had this r mu, from there we constructed this hr with mu star, and then I was just restricting. Okay, so this will be subset of hr, the first thing, this s bar mu bar. Okay, and what I was not saying that how this r is contained in this s bar, right? That you have to see. So the case, so you have already seen this thing. So you have seen in some of the proposition or theorem that r, that each element of r, so let me write in this way, that if e belong to r, this implies e is mu star measurable, right? I think you have seen this thing, and the moment I say e is mu star measurable, this implies that e belong to the set s bar, right? This is there. So this would simply mean that this set r is subset of this s bar, and this would imply that the sigma algebra generated by this r, which is sr, will be also subset of s bar. Why? Because this sigma algebra is the smallest sigma algebra which contains r, and s bar is also a sigma algebra which contains r. So this sr must be contained in this s bar. Okay, so this particular thing, that r is contained in s bar, this gives me, this is the reason why I was drawing this s bar containing this r set. Okay. Okay, so this was all about. So if you notice this mu bar with the domain s bar, this was the domain for mu bar, right, to 0 to infinity, right? This was the domain. Now initially you had a measure mu which was defined on r, and now you have got mu bar which is defined on a bigger set s bar, right? And this is also a measure. Moreover, if you restrict mu bar on the set r, so if you restrict this one on the set r, what you will get is mu. Okay, that the initial ring, the same definition will be true. So if I take any element from here, that so if, what does this mean? This means that if e belong to r, then mu bar of e is equal to mu of e. So what does this say? This thing basically says that this mu bar is an extension of the initial measure mu, right? And this is what we wanted, that initially we had some measure with some domain r, which was the ring, and then from there we constructed this s bar and mu bar. Okay, so in this way this is called that mu bar is an extension of the measure mu. Okay. Now the question is, okay, so what you initially did, that you had some measure mu, you extended to get measure mu bar. Now the next question is, can we extend this mu bar further, right? Okay, so you recall, so what we did, so if you recall that thing, that if we were given a measure mu, we defined outer measure, right? So let us see what the outer measure for mu bar will be. Okay. So mu bar star, so let me recall the definition of mu star first. So mu star of E was nothing but infimum of summation of mu, okay, let's say Ek, such that E is contained in union of Ek, right, where Ek was in R. Okay, so let me write. So R with mu, this is known to you. Okay, and this is how you define this outer measure. Okay. Okay, so in a similar way, now instead of this ring R, you have S bar, mu bar. Okay, now this is known to you, let's say. So from there we can define mu bar star of E, which is nothing but the infimum of summation of mu bar of Ek, such that E is contained in union of Ek, where Ek belong to this S bar. Right, this is summation over K. Right, this should be the definition of mu bar star. Right, now if you again, so this Ek is in S bar, right? So the countable union of Ek, since S bar is a sigma algebra, right? So this will also be in S bar, but due to this one, right? So I can rewrite this as infimum of, okay, let's not write, so let's write mu of F contained in F, and F belong to S bar. Okay, this I can write because anyway, so this I am denoting by F, this union of Ek's, and you know that mu of F will be less than equal to sum of mu of Ek, right? Mu bar of Ek, sorry, so this is mu bar. And so you are taking infimum, so this is good enough to consider that mu bar of F, right? Okay, so this is how you can redefine this mu bar star, right? Now the question is that, okay, so you have this mu bar star and you had this mu star. Okay, so now from here you can define the definition of mu star measurable set, and from here you can say what is mu bar star measurable set. Okay, but I think you have seen a proposition where you have seen that this is equal to mu star of E, right? You have seen this, so let me recall the proposition. Okay, so what was the proposition? The proposition was nothing but this one, that mu star of E. Okay, so this is the definition. Okay, mu star of E was infimum of mu bar of F, where F belong to S bar, and I mean such that E is contained in F. Equivalently, you had also this one, which is mu bar of F. Instead of this S bar, it's enough to take SR such that E is contained in F, right? So using this proposition, you can say that, okay, so this proposition implies that this will be true, right? So there is no question of question mark, so this implies that this will be true, right? So what you are getting, that the collection of mu star measurable set is equal to the collection of mu bar star measurable sets, because the definition is exactly the same. I mean, they are all exactly equal. Okay, so this would imply that we cannot extend mu bar further. So mu bar cannot be extended further, right? Yeah, any doubt?
Yes, sir. We define mu bar on the restricted domain of a mu star.
Yeah.
Yeah. So if we extend, then it will be again become a domain of a mu star. So
Okay, I'll write what you are saying, okay? Then I think everyone will be able to understand. Yeah, can you just repeat? So you are saying that we had mu, so mu star, we restricted mu, the domain of mu star. So mu star was defined on HR. So we restricted it on S bar, okay? So S bar was subset of HR, and we restricted mu bar here, right? Yeah, now what's your question?
sir, my question is, we extend the mu bar.
Now I am asking, so this is my question, that so now suppose you forget about this thing, okay, for the moment. So now this S bar is a ring, I mean in fact it is a sigma algebra. So S bar is a ring and mu bar is a measure, right? Now my question is, can we extend this one? Can we do that? If we, obviously we can extend it, but what will be the outcome, right? So I am saying, so when I had this mu, so when I had this measure, I extended to get new measure mu bar. So the next question is, I have this mu bar now, okay? Can I extend to get something mu tilde? Is it possible? So this is the question, right? So what I am saying, so here what we did, so this was my first step. The first step was to define an outer measure using this measure. So I defined this outer measure using this expression, that outer measure using this measure mu, right? So in the same manner I am defining this outer measure mu bar star using the measure mu bar. And what I am seeing, that this mu bar star is nothing but it's equal to mu star. Is this clear?
Yes, sir.
Did you understand what I said and what your question was?
Sir, then the domain will become again the uh,
Yeah,
outer
exactly.
measure of.
So the domain of, so okay, so what you are saying, so what I am saying, that the measure mu bar star and mu star is defined on h of r. So actually if you start, I think you got, I understood your problem, I guess. So okay, I understood the difference. You are saying that now we are starting with s bar and mu bar, right? So the extension hs bar and mu bar star, this should be the ideal thing, right?
Yes, sir.
But you see, h s bar is equal to h of r, because, so can you guess why this is true?
Sir, because S bar is contained in H of R.
Exactly, because this is there, the set of measurable space is contained in hr. And what is this hs bar? Hs bar is the smallest hereditary sigma ring. So this is the hereditary sigma ring which contains s bar, and h of s bar is the smallest one. So this is contained in h of r. This is there, the first thing, right? This is the first thing, that it should be contained in this one, right? Now can you tell me about the how this is true? Can you recall the definition of hereditary sigma ring? So where should I write? Okay, so what I should say, so this h of r is a sigma ring, the first thing. And H of R. Okay, so this H of R is a hereditary, means it is sigma ring, plus if E belong to H of R, then all the subsets of power of E should belong to H of R. So this is the definition of hereditary sigma ring. Now we have proved that this is there. H of S bar is contained in H of R. Now R is contained in, okay, so R is contained in S bar, right? This is true. So H of R is also contained in H of S bar, right? Or you can see in this way, maybe this would be better way to write. So R is contained in H of S bar, so H of R is contained in H of S, right?
Yes, sir.
So that is why these domains are actually equal. I mean, H of S bar is nothing but H of R. Is this clear?
Yes, sir.
Okay. Okay, so this whole story tells us that, okay, we cannot extend this mu bar further, right? Okay. So actually I'll come to the completeness of these things later on. So far it's that we cannot extend mu bar further. That is for sure. Okay. Okay, so this is the measurable cover. The definition says that suppose you have any element in HR, which is the biggest possible ring you can talk of, right? And suppose F is a measurable one, measurable mu star measurable set, then we say F is a measurable cover. Oh, so there is a typo, it's COVR of E if it satisfies. E is contained in F. That is, what does this mean? This means that the set F covers E, right? This is what it means, that F covers E. Okay, and then what it says, that for all G, so let me write in using the figure. So suppose this is your E and this is your F. Okay, now this F, so the only difference between this E and F is, so the only difference is that this F is measurable, this is mu star measurable, and this we cannot say anything. So this is not known to us. This is just element of HR. Okay, so what it says, this measurable set is a cover of E, and that is why the name is measurable cover. Okay, that the cover about which we are talking is measurable. So this F is measurable cover of E if it is a cover. That is the first thing. The second thing is that you see this space which is F minus E. So it is saying that any subset if you take of here, measurable subset, okay, so for all G which is contained in this one, such that G is measurable, the measure of G should be 0. Okay, so what it actually means, roughly what it means is that suppose this was measurable, in case you suppose the best possible case that E is also E minus F is measurable. Okay, that means that the measure of E minus F is 0. Although this is not possible. The moment I say E minus F is measurable, this should imply that E is measurable, and then we should not talk about any cover of that, because if it is measurable, that is itself a cover of E, measurable cover of E. Okay, so since this is not measurable, what it says that any measurable subset of this grid part is of measure 0. Okay, that means that it's not, I mean the distance is not that big. Okay, so if you have a set, so if you increase a bit, you will, I mean if you increase the size of it a bit, and a bit in the sense that the measure is actually the same, okay, in some sense, so you are getting a cover, I mean measurable set if you extend a bit. Okay, that's what it says roughly. Okay, and what is the proposition? Proposition actually says that if you have any element in HR such that its outer measure is finite. Okay, so using the outer measure, can you say something about this? That, okay, so mu star of E minus F, can you say what is this one? Can you say what should be the value? Because mu star we can define for all the sets, right? The whole HR. So this mu star is sensible. So what should be the outer measure of E minus F? It should be 0, right? Because any subset of E minus F you take, the measure is 0. The measure is 0 means mu star is also 0. Because if you remember, the mu bar is nothing but restricting mu star on something. Okay, so if it is measurable, mu bar is equal to mu star. So for measurable set, right? So E mu bar of E is equal to mu star of E if E is measurable, right? Because it's the same thing. So since each subset of this, whatever subset you take, the mu measure is 0, and I mean when I'm talking about the measurable set, right? Let me check if I'm saying it correct or not. Any measurable set if you take, the measure is 0. Okay, but okay, I cannot say this, right? I should not say this because there could be something which is not measurable, but the outer measure is non-zero. Okay, so I should not say that one, because there could be some set here which is not measurable, okay, and the outer measure is non-zero. That could be possible. Okay, so let's not talk about that. Okay, so let us see this proposition. What it says, that if you have any subset in HR whose outer measure is finite, then there exists a measurable cover. So if you have this E, okay, and this measure of E is finite, then there will exist a measurable cover, that is there will exist a cover F, okay, such that this mu bar of F is equal to mu star of E, right? In this case you can say that this measure, I mean the outer measure of this part will be 0. Okay, so there exists a measurable cover such that mu bar F is equal to mu star E, or since this is equal to mu star of F, so mu star of F is equal to mu star of E. So that is why the difference of outer measure of the difference will be 0. Okay, so what it says, that if you have a non-measurable set then you will get a measurable set which is just a bit bigger than that, not also bigger because the measure are the same, the size is same. Okay. Okay, so this was the meaning of this measurable cover. I hope it is clear. Okay. Okay, so now what we will talk about is completion of. Do you have any question? Okay. Okay, so now what we'll say. So initially what we'll have now, so suppose you have, so okay, let us talk about this first. So you have seen this result, right? That S bar mu bar, this is a complete measure space. I mean, okay, let's not say measure space. Okay, so I'll say mu bar okay, let me write in this fashion only. Okay, so this writing, okay, you can ignore this, but what I mean, it should be clear. So I'm just using this notation as I was using earlier to denote that S bar is the domain of mu bar. Okay, so okay, this is a complete, so the measure mu bar, so in this case measure mu bar is complete. What does complete means? Can anyone tell me the definition of a complete measure or complete measure space? I mean, anything? Do you remember? So what it says, that suppose E belong to S bar, okay, and F, okay, and mu bar of E is equal to 0. Okay, if this is there, then for all F subset of E, F will belong to S bar and mu bar of f will be 0. Right? This is what it means when I say that this measure mu bar is complete on S bar. Okay. Now, instead of this pair S bar U bar, you consider this one, S of R mu bar. So I hope you remember this diagram. So I'll just sketch it again. So this was R, this was SR, and then this was S bar, and this was H of R, right? I said that how this is there. I mean, I am talking about this one. So I said that R is contained in S bar. That is this is how extension means by extension. This is what I explained in the very first slide. And from here you can conclude that S of R is contained in S bar. Okay. So this was the diagram. So okay, so now if I restrict the outer measure mu star on SR, this is also a measure. Okay. So now this, the measure mu bar on this with this domain is not complete. Okay, this is what you have seen. Okay, that this is not complete. Okay, so now this arises a question. Okay, so from here the question is that suppose you have been given a measure with some sigma algebra, or let's say sigma ring. So can you complete it? Is it possible that you can complete it? This is the question. The question is basically that suppose you have this pair S mu. So I mean, okay, so this S is a sigma ring. So how should I? S is a sigma ring and mu is a measure. Okay, this is given to you, let's say. Now from here, can you construct some S bar? Okay, so let's not write S bar. So S tilde or mu tilde. Okay, so S tilde is again a sigma ring, or maybe so, and mu tilde is a measure on that. So is a measure, and this is a complete. Okay, so so this is not complete, and this is complete. Okay, so this is the question, that can we do so? And you have seen that yeah, you can do so. So how you did? Okay, so let me just recall all the things. So S tilde, you defined E, I mean taking this difference with N such that E belong to S and N is subset of A, where A is also in S, I mean this initial sigma ring, and mu of A belong to S maybe such that mu of A is 0. Okay, and you have shown that this is also a sigma ring, and then you define this mu tilde. Let me write it here itself somehow. Okay. Yeah. So this S tilde, and with the definition mu tilde was mu tilde of E difference n symmetric difference should be equal to mu of E, right? This is what you've seen, and this was a complete measure. Okay, this is how you define this and shown this thing. Now okay, what I'll explain, so you have seen this, that the proof of this, how this is sigma ring and how this is complete measure. Okay, so I'll not tell about this one, but what I'll try to explain, that how this S tilde is, I mean how this S tilde is defined. Okay, so can you tell me, so this is maybe the first observation, that how you can say that S is contained in S tilde. I mean this should be the possible thing, right? You want to, you have something which does not contain some zero, I mean whose outer measure is 0, is not there in that set. This is how we mean by complete, right? That if f is there, okay, and it measures should, if it is contained in some 0 measure set, then it should be measurable and the measure should be 0. So you have this, okay. So when I say this S is not complete, what does this mean? This means that there exists some E, okay, and subset of F. So there exists, so I should write in this way, there exists some F in S and E subset of F such that measure of F is 0 but E does not belong to S. This is what it means when I say that it is not complete, right? You understand this one? I mean, these things are clear to you, right? This part? Is this fine to you? I mean, yeah. What do you say? Is this clear or not? I mean,
Yes.
okay. This is fine to everyone, right? So what it means that there are some set. So if you talk about outer measures, suppose, so this implies that mu star of f is 0, right? So mu star of f is 0 and mu star, this implies, since E is subset of that by monotonicity, okay, so let me write it properly. So we have this mu star of f is 0. E is subset of f implies mu star of E is less than equal to mu star of f, which is 0, and you also know that this is always non-negative. So this implies that mu star of E is 0. Okay, so in other words, S mu not complete, this implies, or this means that there exists E in S, or not S, in H of R such that mu star of E, I mean I should write this, or HR is fine, or yeah, okay, HR is fine, I guess. Mu star of E is 0 but E does not belong to this S. Okay, so what it means that, so completeness basically means that if outer measure is 0, it is measurable. That is what completeness means. That if you say that some measure is complete, that means if outer measure is 0, then that should be measurable and the measure of that set should be 0. Okay, okay. So now the question is that you had this S. Now when you are saying this S tilde, so that S tilde, this S is not complete means there are something whose outer measure is 0 but still it's not measurable. So in S tilde, what you should do, you should put those sets in that, right, to make it complete. This is, I mean, completeness means that you want to extend it, you want to put the thing which is not there, right? In usual English sense, if you want to understand that something is missing, you want to put it on that. Okay, so this should be there, I mean this should be expected, and it is in fact true. That, can you tell me from the definition how this is true? Anyone? First tell me whether you have understood, I mean what I have said or not, and then maybe you can tell me the answer. Can you tell me how this S is contained in S tilde? Yeah. Is this not clear? You can tell me, I mean, whatever your views are. Tell me whether you know this or not. I mean, it's not a big deal. Okay.
Sir, if we take a set in S, which is a measurable set,
Hmm.
so S tilde as defined as a mu tilde E of a symmetric difference M is equal to mu E.
Hmm.
Then the set in S mu of E.
Okay, so you don't have to go to the measure. Okay. I mean, see, what you have to show that S is contained in S tilde, right? So you can so let E be in S, right? This should be the starting point, that you choose some element from here and then you show that this is in this one, right? So let's choose E from S, okay? Then you can write E as E symmetric difference with phi, right? You can write in this form.
Yes, sir.
And now this phi also belong to S, right? Because I mean, this is the collection of measurable, so phi is just empty set and its measure is 0, so phi is always there, right? So this phi is there, and if you choose any A, so phi belong to S. Okay, let me write it from here. Phi belong to S, and if phi, I mean, how should I write? So if phi, uh, okay, so this is obviously true, that if any subset of A, I mean, E symmetric difference N, E belong to S, N is subset of A. Okay, this is vacuously true. I mean, phi is any subset of any measure 0 set. That is true. So I mean, this is true. I mean, you don't have to write this thing. Just phi belong to S, and this will show that E belong to S of S tilde. Right? This is the proof that S is contained in S tilde. Now, what I was saying, that this thing S tilde is just adding those sets which has outer measure 0 or which is subset of some measure 0 set, right? So if you take now E to be phi, so choose E equal to phi, then E symmetric difference with N is nothing but N, right? And this N belong to S tilde, right? And if you notice, this measure mu tilde of E direct sum N is equal to mu of E, which is mu of phi, and which is 0. So this is nothing but mu tilde of N. So now you understood that these N I mean, these sets, these N, this type of set which was subset of some measure 0 set which was not there in S, it was not there here, right? Because it is not complete, means that there is some set N which is contained in some measure 0 set, right? So here what we are doing, we are adding those sets N in this S tilde. And because of such constructions, this S tilde with this measure mu tilde is complete. Did you get this point? I mean, see, this is important in the sense that this is how it is done. I mean, the proof is okay, you understood the proof, you remember the proof, that is fine, but this is how we are doing it. This construction is telling you that this will incorporate all those sets which was not there in S, because of which S was not complete. So S had some missing element, and the missing elements were of this type. This type of sets were not there, which are subset of measure 0 set, but still they are not measurable. And we put these sets in S tilde, which makes this S tilde complete. Okay. So this is the story about this S tilde. Is this clear?
Yes, sir.
Okay. So if you have no doubt, I can proceed further. Okay. So you saw this thing. So let me draw that figure again. So you had this R, then you had this SR, and then you had this S bar. This with a mu bar, and this was mu, right? So you saw in the lectures that this is not complete and this was complete. Okay. Now now you can try to complete this to get S tilde mu tilde. I mean, I can start with this thing, and using this step, I mean this sort of thing, this type of defining S tilde and mu tilde, I can get this extension, right? Now the question is, this completion of S R mu bar, is there any relation, or the main question is it equal to S bar mu bar? Because we know that this we cannot extend further, okay, and this we can extend to something. So will these two be equal? This is the question. Is this equal? And the answer is yes, if mu or mu bar, whatever, is sigma finite. Right? Because mu sigma finite will give mu bar sigma finite. So I mean, this is the thing, that the measure with which we are starting. So let me write both mu or mu bar. I mean, it's the same thing. I mean, mu or saying mu bar, this is sigma finite. Okay, so this is true. You have seen this one. So do you know any counter example when this mu is not sigma finite, then the extensions are completely different? Do you know any, I mean, example to that? Okay, you don't know? Okay, so let me give an example. Okay, so suppose this X, any uncountable set, okay. Okay, this is any uncountable set, and consider this S, which is subset of X such that E is countable or E complement is countable. In the last session, I have shown that this is a sigma ring, right? Okay. In fact, it is a sigma algebra, so it's better to write the best one. Okay. So this is a sigma algebra. Now take mu. I mean, this is the counting measure, okay? So counting measure, you know, I mean, if it is finite, if the set is finite, then the measure is just the number cardinality of that set. In case it is infinite, and the mu will be taking the value infinity. So let me, so mu defined on this S to 0 infinity, mu of E will be the cardinality. So this is number of elements in E if E is finite, and infinity else. Okay. Okay, so this is the measure what we define on this. Okay, now by the definition itself it seems that this mu is complete. Can anyone tell me how this is complete? So I am saying that this is a complete measure. This is obvious, right? Okay, just tell me this. If mu of E is equal to 0, what does this mean? By looking at this definition.
E is empty.
E is empty, right? So now since mu of E equal to 0 implies E is in empty, that means there is only one set which is of measure 0. I mean, there is no subset of this further. So there is no, I mean, there is no question of complete measure as such. It is automatically complete, right? Okay. So you have this one. Now, since this is complete, we cannot extend it further, right? Okay. So this is a complete measure. Okay. Now, now what you do, this S, now start with this one. So S mu, this is the same pair. So this is one way. So now start with this pair. Now what you do, so this is my given to you. Now it's given to you. Now if you start with this as a ring, S as a ring, okay. So it is a anyway sigma, so sigma algebra, so it is a ring, and this is a measure given to you, okay. So from here you can go to H of S, right? And what will be H of S? Can you tell me? It's quite easy. No? So see the definition of S. Can you tell me what will be H of S? Okay, can you tell me X belong to S or not? Is this true?
No, sir.
Because X complement is 5. So X belong to S. As X complement is 5 and this is countable, in fact finite, so it's there. So this implies X belong to S. Now this power set of X then is equal to H of S, right? Because what is hereditary means if something belong to this, then the whole power set of that should belong to H of S. And in fact this is the largest possible hereditary sigma ring, so it is in fact equal. Okay, so this HS is nothing but power set of X. Okay, and we define, so since this is there, so you can define H and mu star you can define here on this thing by mu star of E. You can define it as mu of E. So this is for all E belonging to P of X. I mean P of X is nothing but H of R. I mean not R, it's S, right? This is how we define mu star of E. You can check. This is there. So mu star of E is equal to mu of E. Now what does this mean? So what does this imply? See, mu star is in fact a measure. So this outer measure is no longer an outer measure. It is actually a measure. So this implies that all elements of Px are measurable, and that is the S bar. If you recall, I mean S bar I am saying when we started with this R, from there we get HR and from there we get S bar. I mean the set of measurable set is equal to P of X. So see here this S tilde, so this is complete measure, so we cannot extend it further. So this, let me write in the next page maybe. So this S tilde is equal to S and mu tilde is equal to mu, but this S bar is equal to power set of X. Okay, and uh, just a second. Okay, and this mu tilde, sorry, mu bar is equal to mu. Okay, so this is there. Now, so is this clear to you? So this S tilde is clearly not equal to S, right? Is this fine? Tell me if it's fine or not. Yeah. Okay. If this is fine, now let us proceed further. So see, just recall the main thing what we wanted to study initially, that we wanted to extend the notion of integrability of a function, right? So we knew the theory of Riemann integration. We wanted to include more function which can be integrated in some sense, right? So we wanted to define this Lebesgue integration, and the Lebesgue integration was defined using the inverse image. So by partitioning the range. While doing so, what we encountered, that there were some set which was not, I mean, we didn't know how to measure the size of that set, like this one or the complement of this, whatever. So we knew that there were some set which we cannot measure, and that is why we want to define a measure called Lebesgue measure. And to define this Lebesgue measure, we started the theory of measure, that what a measure is, and some related stuffs, that if some measure, what do we mean by complete measure, and if some measure is not complete, can we complete it? If we can, what is the process of completing that, right? So this was all about till now. Now we will define this Lebesgue measure, that what this Lebesgue measure is. Okay, and then using this Lebesgue measure, we'll go for the function which can be integrated, and so on. The theory will go forward. Okay, so let us first see what is this Lebesgue measure. Okay, so now to construct a measure, what we have seen, that we should have some idea of measure. So we should have some pre-measure, and from that pre-measure we defined outer measure, and from that outer measure we defined the measure or measurable sets, right? So when we are in R, although I have given some idea, that we have some notions of length of interval, right? And using that length of interval, I mean, we saw that the length function is actually a measure if we define it on a proper set, right? So what we'll do, so first question is what is R and what is mu? This is the pre-measure. What is this one? This and this. The moment we get this one, from here we will get h of r mu star, and from here we will get s bar mu bar. The same process. I mean, this part is nothing. The main part is to determine what is r and what is mu, right? Okay. So let's start this whole discussion about this Lebesgue measure. So what we can do, so we define this initial P. Okay, P will be the collection of A B belong to R. This is the initial set P. Now R you can define as the collection of finite unions of such sets. So it is basically union of EI, where EI belong to R. Okay, so we are just taking finite. So I equal to 1 to n. You know that this is a sigma ring, right? And now the question is, so here we know that we can define measure. So mu of AB, I can define, oh sorry, so mu of this interval AB is B minus A. This is what we define. So this is the definition. Now the issue is, okay, so for this set we have some notions of measure, but for measure you have to, the domain of measure should be some sigma ring and not just a collection, right? This is how we define measure, and measure from some ring to 0 infinity. Okay, so this is a ring, in fact this is a, okay, so this is just a ring, not a sigma ring. Okay, so this is a ring. Now our idea should be that using this thing, what is known to us, we should define some measure here. So how we can define? So suppose, so I am just taking n equal to 2, I mean just to make you understand how we are defining. Suppose this is A1, B1. Suppose this is A2, B2. This set, this A1, B1 union A2, B2, this belong to R clearly. Now how should we define this measure for this set? That is the question, that A1, B1 union A2, B2. What should be the thing? So in case, suppose this, instead of here, if A2 was here, then we know how to define. We'll just sum the length of this interval and this interval, right? So I'm saying, if this A1, B1 interval and this A2, B2 interval were disjoint, then we could simply sum this length and this length to get the measure of this one, right? But now the problem is that this is not the case. I mean, these need not be disjoint. Just a second. Okay, so this did not be the case. So what we can do, we'll use the same. So when they are disjoint, we know how to do that. So what we'll do, we'll try to make these things disjoint. Okay, so how we'll do in this way. Suppose this is there, so I'll define this, let's say this till this, and then from here to here. We can do this way. So we are partitioning in two things. So what I'm doing, so this is one, this is second. These are disjoint, right? Because it's closed from one side, it is open from the other side. So these are disjoint. Now this is the same, I mean this was my interval, right? A1 union B2 was this one, and this is covered by this I1, I2. So this thing I can write, this is measure of I1 plus measure of I2. Now the question is can it be a definition? So it seems that this should be the ideal definition what we should start with, right? But the question is, if this is the definition, what if, suppose I chose this partition but someone else can choose this one. So let's say this from here to here, and then from here to here, and then from here to here. This is also one partition. I mean partitioning the things in disjoint subsets. So in that case, if I write this is J1, this is J2, this is J3, then according to this definition, it should be also mu of J1 plus mu of J2 plus mu of J3. So this is the question of well-definedness. Okay. So this is the question of well-definedness. That okay, the logic is clear, that if they are not disjoint, we will make it into disjoint sets. Now the question was that we can make them disjoint in infinitely many ways, right? I could have even done here, and then, I mean, there are so many ways to make them disjoint, right? We could have even added one more thing. We could have we could have added this extra thing as well. I mean, we could have partitioned in 4 intervals, let's say. right? So the question is that if it is a definition, if we want to use this definition, it should be well defined, that in whatever way we partition the interval, I mean this set, in whatever way we partition this set, the sum of those measures, I mean the sum of those length should be equal, right? And in fact you have shown in the lectures, you have seen that mu is well defined, and mu is a measure as well. We have seen these two things, right? So you have seen that okay, this mu, the way I have defined here, is well defined, that it is in fact a measure. Okay, so this is how we can start. So this is r, so r is this one and mu is this one. Okay, now from here, the, I mean this path is exactly the same. Okay, so from this r mu we will go to hr and then mu star, and from here I will restrict to s bar mu bar. Okay, so is this clear? I mean this will be the process till here. If it's clear, then I'll go further.
So
Yeah.
ring, the ring is how to define the ring as the union of EI.
So it just says that suppose I choose some element E from R, this element should be some finite. So from 1 to n, it should be of the form AI, BI. I from 1 to some n. I mean it should stop somewhere. This is the definition of the ring.
Okay, sir.
I mean this was your question or something else?
Yes, sir. I could not understand how to define the ring.
So this is the definition, that any element of the ring will be of this form. Okay, you didn't see this thing, I think. Okay, I talked about it in the first session as well, but I didn't talk it in a very well manner. But now, I mean, you can in fact show that this is a ring. So do you want to see how this is a ring? I mean, you want the proof of how it is a ring, is it?
No, sir. It is in the assignment.
Yeah, you can check. It's very manual that it is a ring, but the definition is of this form. So if you don't want, this EI is of the form AI, comma BI. Okay, if you want in this fashion. Okay. Okay, so from here we want to go here, reach here, right? So see this one. So let us first see. So okay, I'll go. So the first thing is to find what will be my HR. Okay, and then I'll define what is mu star. Okay, so I mean we know that such things will exist. Now I'll try to make it more precise, as far as, I mean, to what level it is possible. Okay, so let us first see. The sigma algebra SR. I mean the sigma algebra generated by this ring R. Okay. So see this set of real numbers, I can write it in this form, n from n plus 1, and this n is varying over z. This I can write, right? The real numbers can be written in this fashion, right? Now, sorry. So what does this mean? This thing, where does it belong? It belongs to R, right? And so, since this is a countable union of elements of R, this belongs to S of R. Is this clear how it belongs to S of R? this belongs to R. This means that this is in S of R, and this is countable union of elements of S of R. So it is also in S of R because S is a sigma algebra. Since S of R is a sigma algebra. Yes? Tell me if it's not clear. Okay. So we can say that this R whole set R is in the sigma algebra. And that is why this implies that the so this would imply, so if I go one step further, this would say that this is in H of R as well, because H of R is a sigma algebra and it contains more sets. I mean, if E belong to H of R, then whole power set of E should be in H of R. So this is a much larger set H of R. Okay, so this implies, I mean, if I combine this all together, that R belong to H of R, and this implies the power set of R is in H of R, and this would simply mean, in fact, that H of R is equal to P of R. Okay, so this R is the ring R, I mean what I defined, and this R is the set of real numbers. Okay, so this is my H of R. So all the subsets of real number, okay, we can define mu star, I mean outer measure. So outer measure can be defined for any subset of real number. Okay, so not just outer measures, this will be called Lebesgue outer measure, and this will be called Lebesgue measure. Okay, so what it says, that any subset of real number R, we can define outer measure for that. Okay, so how will we define? So for all E belonging to power set of R, mu star of E will be nothing but infimum of summation of mu of I k from 1 to infinity. Okay, let me not write infinity, just k, such that E is covered by union of Ik, and Ik belong to R. Right, this will be the definition of mu star, where this mu of Ik is nothing but the length of Ik. Okay, is this fine? I mean, this is just the definition what I gave.
Yes, sir.
Now can you tell me that such cover exists? In other words, can you tell me that this set is non-empty? I mean, if you choose any subset of R, it has some cover. Okay, I mean, such covers exist, and so such a summation exists, and then because to take infimum you need the set to be non-empty, right? Yeah, in fact, so you can see this, right? It is clear from this expression. We know that R is equal to n belonging to Z, n to n plus 1, and this would imply if you take any subset of R, you just take intersection with R. So R, so E is equal to E intersection with R, and this is equal to n belonging to Z, n to n plus 1 intersection with E. So you see, this E is covered by these many sets. So such cover exists always, and so such summation exists, and so this infimum also exists. Okay. Okay, so this is how we define H of R. Now this S bar, okay, so this S bar I will denote by L of R. So L of R means the Lebesgue measurable sets. So L of R is S bar, okay, which is A belonging to H of R, which is power set of real number such that A is mu star measurable. Okay, this is my S bar, and okay, so this m1 of A will be this mu star of A, right, for all A belonging to S bar. I mean, this m1A is the measure. If you want to see in the analog of the earlier context, this is mu of A, I mean the measure. Okay, so this is Lebesgue measure in R. Okay, if I write m of n, then Lebesgue measure in Rn. Okay, okay, now this was all about how we can do the construction. Okay, okay, so now, okay, so let us talk about Borel sigma algebra. So I forgot to tell you, maybe I should say it here. So you remember that, okay, we defined this S bar, and then there was another set S of R, which is sigma algebra generated by R. This S of R is called Borel sigma algebra. Okay, so see, earlier when we were constructing this S bar or H of R, whatever, and I mean this more specifically this S of R, we were saying this is a sigma ring, right, in the earlier construction. But now I'm saying this is a sigma algebra, and the name is because of the mathematician. Okay, so this name does not make any sense. I mean, it does not have any meaning. But sigma algebra, you see why it is sigma algebra. The reason being that this line, that R belong to S of R. So this S of R was sigma ring earlier, but since the whole set X, I mean this was my X, right? This is X. If you compare with the earlier notations, so this whole space, I mean the whole set belong to S of R. So that is why this S of R is a sigma algebra. Okay. Okay. So this is why this is called Borel sigma algebra. Okay, so anyway. Okay. So Borel sigma, so let me write it here itself. So this I will denote by B of R. Okay, and this will be S of R, and the name is Borel sigma algebra. Okay, okay, so this is a Borel sigma algebra, and any measure if you defined on BR is called Borel measure. So a function, a measure which is defined on B of R, this set, is called a Borel measure. So Lebesgue measure, if you restrict on the Borel sigma algebra, is called Borel measure. Okay, so this BR with M1, so this M1 will be called Borel measure, and this L of R with M1, I mean when I change the domain, this is Lebesgue measure. Okay, okay. So this is just the name. Okay, so every countable set in the real number is actually Borel measurable, and the Borel measure will be equal to 0. This is, you in fact you have seen in your class lectures, right? So every countable set, if you take, it is Borel measurable. Okay, so if E subset of R such that E is countable, implies E belong to B of R. Okay, and this implies E belong to L of R. Now this, okay, so let me first state the result. E belong to B of R, and M of E is 0. Now M is any measure. Okay, in particular I am choosing Lebesgue measure. I mean Lebesgue measure on the set Borel sigma algebra. This means M1 of E is 0, and this in fact shows that okay, this is obvious actually. So if something is Borel measurable, it is Lebesgue measurable, right? Because we know that this was S of R, then this was S bar, and this was R. So this is Borel measurable set, this is Lebesgue measurable. In fact, you will see that this B of R is strictly contained in L of R. I mean there are some set which are Lebesgue measurable, but they are not Borel measurable. Okay, so this you will see later on. So this result says that every countable set you choose, any countable set, it is measurable and its measure is 0. So you remember this thing, q intersection 0 1. I mean, in the last session I said that the measure of this set is 0 because this is countable. This comes because of this thing. Okay, so the measure, I mean, the example could be that measure of q, let's not intersect with 0 1, q is 0 in fact, since the rationals are countable in real number. Okay, now okay, so let me mention one thing, that this was my p. You could actually start with p as this one as well, a infinity, a b closed. I mean, any type of set if you start, you will get the same story. Okay, so the theory will be same in fact, and that is there. Okay, so that is one result. So let me mention it somewhere. uh, okay, I mean, I just said it. So instead of p with this half closed half open, you can choose any other type of interval, either of the type a infinity, I mean, a infinity. So let me write this way. So suppose p1 is ab belong to r, p2 is, let's say, ab belong to r, p3 to be a infinity, a belong to r, and so on. Okay, so the Borel sigma algebra generated by PIs, which means it is a sigma algebra which contains this set, is equal to BR. Okay, so this, I mean, the things will remain same, and in fact you have one more. So this is one result. The other thing is that B of R is equal to sigma algebra. Okay, so let's not borrow. So sigma algebra generated by PIs. So for any I, is equal to the Borel sigma algebra. So Borel sigma algebra is also sigma algebra generated by any open set. I mean, generated by collection of open set. So generated by collection of open sets. So suppose you have a collection of open set which is called S. So let me write in this fashion. Generated by S, where S is collection of open sets. Okay, so if you have a set or P, okay, so let me write some P tilde to be more. So P tilde, if you have any collection of open set which contains open subsets of R, if you think of a sigma algebra which is generated by that P tilde, will be the Borel sigma algebra. Okay, so this, I think this you have seen in the lecture, and this is also easy to see because you can write AB as AB minus A. I mean, each of the element here can be rewritten in terms of closed A and open B and vice versa. Okay, so that is there. So you can think about this one. This you have already seen, and you can think about this one. Okay, it's the same. And okay. Okay, so this is one remark. So I think this you have seen in the lectures as well, that the Lebesgue measure. So suppose we are in R2. Suppose this is R2. Okay, so so let me start with R itself. So what we know, Lebesgue measure M1 of E. If I talk about M1 of some set E, so obviously E is subset of R, right? So E is subset of R. When I say M1, that means E is subset of R1. Okay, so this means this M1 of E will be length of E1. Okay, this will tell you how much length or this length in one dimension. In one dimension, the measure is nothing but the length. But if I say m2 of E, okay, and E is subset of R2, then what should it measure? If we are in two dimension, the measure is basically the area. So this is basically area of E. If I say m3 of E, where E is subset of R3, it should measure the volume. In fact, it measures volume of E. Okay, and so on. I mean, if you go in higher dimension, it will be measuring the size from all the directions. Okay, so what this line means, that if you are in R2, let's say this is my R2 space, if you take any line of this sort, okay, if you choose any line, so let's say this is E, then m2 of E is 0, because if you want to see in a common sense that it is covering, I mean, it is uh, what should I say, it is not uh, actually it is not covering any area of R2. In terms of area, it has measure 0. I mean, its size in terms of area is 0. Lengthwise, it has some measure. So if you want to calculate m1 of E, this is obviously non-zero, but m2 of E is 0. Okay, so this is what it means. So if you take any proper subspace, now proper subspace means that the dimension of E is strictly less than n. So the result, if I want to write that if E is subset of Rn subspace, proper subspace, no, proper subspace, this means that the dimension of E is strictly less than n. Okay, then m n of E will be 0. Okay, this is what it means. Okay. Okay, so let us now see the properties of Lebesgue measure one by one. So if A is any non-empty open set, then the measure of A will be strictly greater than 0. I mean, it cannot be 0 if you have any open subset. Okay, can you tell me the reason? So suppose X belong to A. Now since A is open, so this is since A is non-empty, so X belong to A. Now since A is open, there exists delta greater than 0 such that X minus delta, X plus delta is subset of A. If you want to go in a general setup, then it would mean in Rn I am saying B delta of X is subset of A, and this would imply the measure of A, Mn of A, is greater than equal to Mn of the ball, and the measure of this ball is nothing but delta raised to the power n, right? And this is greater than 0. So if there is something, some open subset, then the measure will always be strictly greater than 0, because if it is open, that means it contains some interval inside it, and because the interval has length positive, so the by subadditivity the measure of the set will be greater than 0. Okay. The second property is nothing but the contrapositive of this one. So you know about the contrapositive, that A implies B means not B implies not A. So this is what contrapositive means. A implies B, so this and this are equivalent. Not B implies not A. So these are equivalent thing. Okay, equivalent, both are equivalent. So okay, leave equivalent. Okay, leave it. This sign. Okay, so this is what it means by contrapositive. So what it says, so this is done. Now from here you can conclude about this one, that if there is something which is of measure 0, then it cannot contain any non-empty set. If the measure is 0, it cannot contain any non-empty set. You can see as an example this one, that measure m1 of q, you know, is 0, right? And you know that rational number are dense in, I mean, irrational and rational are dense in R, so it cannot contain any I mean, there is no interval of this form AB which is contained in Q. This is not true. Which, I mean, it's an example which explains this thing. Okay. Okay. So this is there. So if some measure, so I should have left it written. So if something has measure 0, it cannot contain any non-empty set. Okay. Okay, so this is the another one which is, I mean, direct conclusion for this one. So Mn of E0 implies E contains no non-empty open subset. So if you see E complement, then E complement is dense. Why? Because see, so do you understand the meaning of dense, right? So if you choose any element from the set, so dense means if you choose any element from X and any delta, so B delta X will contain some element. So there exists Y belonging to E complement intersection B delta X. Okay. So see, so this is what it means by dense. Dense means that if you choose any point from the space X, if you take any neighborhood, in that neighborhood there will be an element of E complement. Okay, so there will be an element of E complement which is in that neighborhood. Okay. Okay. So how is it true that you know E cannot contain any open set? So this is open set. So let me see the proof. So if you choose X in X, so B delta X, this is an open set, right? This is an open set, and B delta X is an open set, and you know that any open set cannot intersect E. I mean, it cannot. So B delta X is not contained in E, right? It is not contained in E means that B delta X, there is some element in this which is not in E, so that is in E complement. So this implies this intersection is non-empty. Okay. So this is how we mean that E complement is dense, and this proof of this one is easy because you know X is nothing but E union E complement, and by additivity M of X Mn is Mn of E plus Mn of E complement, and we know that Mn of E is 0, so this means this is Mn of E complement. Okay, so this is easy. Let us now come to the third property. Okay, so I would like to ask this question to you. So do you think that any density and measure has any relation? So you saw that that countable, this rationals are countable and they are dense, but the measure of rationals are 0. I mean, the set of rational, the measure is 0. So is there any relation you can see so far, that if some, let's say it is dense, that would imply that measure should be this one? Do you have any idea about this one? Okay, so I mean, see, this Q is dense in R, and R minus Q, that is irrational, is dense in R, but measure of Q is 0 and measure of R minus Q is infinity, right? So this says there is no relation as such. So measure can be anything. Measure has nothing to do with density of a set. Okay. Okay. So now the question is, what did you see? That if A is open subset, the measure is positive. So is the converse true? That if the measure of some set is positive, will it contain a non-empty open subset? So this is the question. This is the converse of this part. It says a non-empty open subset implies measure is positive. Now the question is, measure is positive, does it mean that it will contain a non-empty open set. What do you say? Is this true? Any guesses? Yeah. Okay, so tell me about this one. You saw that Q complement intersection 0 1. That is irrational in the interval 0 1. What is the measure of this one? This is 1, right? Because the measure of Q intersection 0 1 is 0. So by this property, its complement will have measure equal to 0 1. Since measure of Q intersection 0 1 is 0, right? And this is equal to 1. So this measure is positive, but still Q complement in the whole real number actually. In fact, in particular in Q complement intersection 0 1. So if we restrict to 0 1 interval, the irrationals are dense. The rationals are also dense. So if you take any open interval, it will contain rational as well as irrational. So no interval, so no open interval AB is subset of Q complement intersection 0 1. So this is not true. That if the measure is positive, it need not contain any open set. In fact, here you can see it cannot contain any open interval as well, which is an example of open set. Okay. Okay. Now it says that any compact set if you take, it has a finite measure. The reason being that compact subset of R, okay. So it should not be R, it should be the real number R. Okay, so let me correct it. So this is a real number, or Rn maybe you can take. Okay, so compact means bounded. Bounded means that if you are in real number, it is contained in some bounded interval. If you are in R2, it is contained in some bounded square. If you are in R3, it is contained in some bounded cube. Okay, and so on. So bounded and so finite measure by subadditivity. Right? Okay. Okay, so since we are not left with much time, so do you know the construction of Cantor set? Or should I explain you again? Yeah. What do you want? Do you want to know the properties? So I was planning to tell you the construction and then the properties of Cantor set. So if you have understood very well, then I will not. If not, then I'll explain. Can you tell me? And this you can answer, right? What do you want? Maybe you can tell. Tell me whether you want it or not. It's just a simple question.
Yes, sir. I don't know about how to construct Cantor set.
Okay, okay. Okay, so I'll just explain you what it is about. Maybe the exercises what I have planned to discuss, that maybe either I'll write it up and then I'll send the notes, or maybe in the next class I will discuss. Okay. Okay. So suppose what is there. So Cantor set is basically, so okay. So so far what you know, that you have a countable set, then you know measure, or more specific countables. Let me write it more proper to the Lebesgue measure. set up countable subset of Rn or R, let's say, implies Lebesgue measure is 0, right? Now the question is that suppose mn of E is 0. That means the Lebesgue measure is 0. So the question is that does this mean, so this is the question, that E is countable. This is the question, that if the measure is 0, can we say that the E is countable? Okay, and the answer is no. Okay, so you will see that the Cantor set C is uncountable and okay, so Cantor set C is uncountable and the measure m1 of C is equal to 0. Okay, so this C is subset of 0 1 more, I mean we are in R. Okay, and that is enough to give a counter example. Okay, so let us see how to construct the Cantor set. Okay, so I'll just come from washroom, just wait for a minute. Okay, so this Cantor set is an example of an uncountable set which has measure 0. Okay, so how do we construct that? So suppose this is the interval 0 1. Okay, now what you do, you partition it in 3 parts, in 3 equal parts. Okay, so this is, let's say, 1 by 3, this is 2 by 3. Okay, and then then what you do, you just remove this part. Okay, this part you delete. In that case, what you get, you get this one, right? So yeah, so if you remove this part, you are left with this part. Okay, so these are closed. Okay, so you have this closed interval 0 1. Okay, again you repeat the same process. Now what you do, again you divide this part in 3 equal halves. So this and this, sorry, this one. Okay, now and this is 2 by 3 square. This is 1 by 3 square. This is 3 by 3 square. This is 6 by 3 square. So this is 7 by 3 square. This is 8 by 3 square, and this is 9 by 3 square. Okay, so again what we did, we just partitioned this interval and this interval in 3 equal halves. So this is 3 equal half of this part, 3 equal half of this part, and now you just remove the middle part. This part you remove again. Okay, again what you get, you get this one. So you get this, 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 and this. I should extend this one, this one, right? Okay, so let me write. So C1, so I am defining this C1. C1 is nothing but this closed interval 0 1 by 3 union this 2 by 3 1. Okay, this C2 is 0. So C2 is 0 1 by 3 square union 2 by 3 square, and then 3 by 3 square, which is 1 by 3 union this 2 by 3 7 by 3 square union this 8 by 3 square, and then 1. Okay, in a similar way, this again you can partition this. Okay, in 3 halves you do, and then just remove this part, this part, and then you will get C3. So this will be union of 1 2 3 4 5 6 7 8 intervals, right? Okay, so now just try to note some, how we are constructing. So just note this part. This is union of 2 intervals. The length of each interval is 1 by 3. So 2 interval of length 1 by 3, right? Again, in the second go, this 2 interval is further partitioned into 2 intervals, right? So this 0 1 by 3 is partitioned in these 2 halves. This 2 by 3 1 is partitioned in these 2 halves, right? So this C2, okay, so this C2 is 4 intervals, in fact closed, of length. So this was the length of 1 by 3. We further partitioned in 3 equal halves. So the length of each interval will be 1 by 3 times 1 by 3, right? So this is length of 1 by 3 square. In the same way, C3 is, so this is, okay, so I should write 2 square intervals, right? So 2 interval again partitioned in 2 intervals. So it is 2 square intervals. Here union of 2 cube intervals of length, so each of length 1 by 3 cube, right? So is this clear? I mean this part? Yeah, okay. So this is fine now. So in this way we continue. So overall what I can say, that this CK is union of 2 raised to the power k closed intervals, each of length 1 by 3 raised to the power k. Now this CK is union of finite union of closed sets, right? Closed interval is also a closed set. So it is finite union of closed set is closed. So this implies ck is closed. And also notice that when I am saying that we are defining this ck, they are union of disjoint intervals. I mean this. So if you say these are disjoint. So ck is closed, and m1 of ck, if you calculate, it will be sum of these k intervals. So it will be sum of 2k intervals since they are disjoint, and each interval has a length 1 by 3 raised to the power k. So this into 1 by 3 raised to the power k, so which is 2 by 3 raised to the power k. So is this clear, this part? Yeah.
So basically we add the all the length of the interval,
Okay,
the
so
measure.
because they are disjoint, right? So if you see, if I ask you that what is measure of this c2, then the measure of c2 will be sum of this plus this plus this plus this, right? Because they are disjoint. And yeah,
No, sir.
what is your question?
Yes, sir. I got it.
Oh, you got it. Okay, okay. Yeah. So this is what I mean. So measure of the ck will be 2 by 3 raised to the power k. Okay. Okay. So this was about ck. Now what is the Cantor set? So Cantor set, c is equal to the intersection of ck, and k is varying from 1 to infinity. Okay. So you intersect all those ck. Okay. Now this ck were closed, each ck were closed. Now countable intersection of closed set is also closed. Okay, so that is why, okay, that I think in the next slide I'll tell. Okay, so since this is countable, countable intersection of closed set, in fact any arbitrary intersection of closed set is closed, so that is why c is closed. Okay, now if you see m1 of c, m1 of c is m1 of intersection of ck. Now you know the property, that continuity property. So you see this one first, that each ck is this sequence ck is decreasing. That is c2 is contained in c1, c2 contains c3, and so on, right? So this ck is decreasing sequence, and measure of c1 is finite. I mean measure of ck is finite for all k. So by continuity you have that this should be limit of m1 k going to infinity, m1 of ck, by continuity from above, continuity from above, right? This is there. Now this is 2 by 3 raised to the power k, so the limit will be, so this is limit k going to infinity 2 by 3 raised to the power k, and this is 0, right? So this is less than 1, 2 by 3 is less than 1, so limit will be 0. Okay, so m1 of c is 0. So far we have got that m1 of c is 0, but we don't know whether this is countable or not. That we have to make sure, right? Because what our goal was, our goal was to show that this Cantor set is of measure 0 and it is uncountable, right? So we have shown that the measure will be 0. Okay, and now we have to show that it is uncountable. Okay, okay, so see this property first, that c is nowhere dense. So do you know the meaning of nowhere dense? Yeah, so nowhere, yeah,
Closure has empty interior.
okay, closer. So e is nowhere dense if interior of e closure is phi, right? This is what it means by, okay, Okay, before going to this property, can you tell me some elements of C? So how can you say that this is non-empty? Can you tell me some element which is in C always? From the figure, can you tell me?
Zero.
What?
Sir, zero element.
Exactly. So any of the endpoint, if you see this 0, this 1, this, what are the, this 1 by 3, 2 by 3, 1 by 3 square, 7 by 3 square, what all the endpoints. So endpoints are always there, right? Because we are partitioning the interior part always. So interior, I mean the endpoint is always there. So see, endpoints at each level, belong belongs to C. Okay. Okay, so now the question is about nowhere dense, that this is nowhere dense. Okay, so let us see. So we have to prove that the interior is empty. So let's say, let X belong to interior of C closure. Okay, now since C is what, C is closed, so this means that this is interior of C. Right? Since C is closed, C closure is equal to C. So suppose X belong to interior of C, then this implies that there should exist, so there exists delta greater than 0 such that B delta of X should be contained in C closure, because interior is what? Interior means that if you have some point in the interior is in fact open set. So if something is inside the interior, then you will get a neighborhood which will be contained in the set, right? This is by the definition of interior. If you have some point in the interior, you will get a ball around that point which will be contained in the set. Okay, so this is by definition. Now this would mean that measure of C1, C closure, is greater than equal to this delta, and this is positive, which is a contradiction, right? Because we know that the measure is 0, so that's why it's nowhere dense. Yeah. Okay, so this was just an additional comment. This we will not need for our purpose. So this is just an additional comment. Okay, let us see that C is perfect set or not. So this is first thing. So do you know the definition of perfect set? Yeah, can you tell me? Okay, so perfect set basically means that it is closed. Okay, and there is no isolated point, plus no isolated point. So all the point will be limit point. Okay, so isolated point basically means that if X is said to be isolated, if you take any neighborhood, it will not contain any other element of that set. That means that is, I mean, isolated. It is like, what does isolation mean? That you are in isolation. That means in your neighborhood there is nothing. So this is what it exactly means. That it, so if a set is closed, and if it has no isolated point, then that set will be called closed, I mean perfect set. So you already know that C is closed. Okay, so let me prove this one. So C is closed. Okay, now the extra thing is to show that any point if you take, it is a limit point. I mean it cannot be an isolated point. Okay, so choose X belonging to C. Okay, and take any neighborhood. So okay, so X belong to C, what does that mean? First thing, that if X belong to C, that means it belongs to each of the C case, because C is intersection of C case. So C is intersection of C k. This means X belong to C k for all k belonging to 1, 2 and so on, right? Okay, I think this is there. Now if you choose any delta, so for any delta greater than 0, see this set B delta X intersect with this ck and then subtract X. Okay, so if you choose any element from the Cantor set And if you consider a ball around that set, okay, then, and if you intersect with ck, so it is always non-empty. Okay, so this is always there, that is it is non-empty. Okay, and this would imply that any all I mean all points of c are limit points. I had few exercises what I thought I'll discuss. Okay, I'll see. Either I'll write it out or I'll discuss in the next session. That would be a good option. I'll see what I can do. Okay. Okay then. So, do you have any doubt? You can ask me. Or is there any doubt? Okay. So, if there is no doubt, so I'll just stop here.